Exercise 618 is asking about carbocation rearrangements. So let's break that down. Let's rewind and talk about first what a carbocation even is, and then how it behaves. An ion is an atom that has a charge. You could have a positive charge or a negative charge. Ions that have a positive charge are called cations, and ions that have a negative charge are called anions. You can remember that because the T in cation sort of looks like the positive charge. Now, if the cation is on a carbon, if the positive charge is on a carbon, then that is called a carbocation. So a carbocation is just a carbon that has a positive charge on it. Now remember, carbon, if you calculate the formal charge for carbon, it only has a positive charge when it has 3 bonds. So if carbon has 3 bonds and no lone pairs, then it's in group 4A, 4 minus 3 bonds, 0 lone pairs, 0 dots. So that's positive 1. So, and let me draw that in with the, so there. Okay, so carbocations are carbons that have a full positive charge on them. They are on carbons that have only 3 bonds. Now there are different types of carbocations. The 3 most common ones are classified according to how many carbons they're bonded to. So for example, you could be bonded to just one other carbon, and the rest would be hydrogens. In that case, the carbocation is classified as primary. In other words, the carbocation is just bonded to one other carbon. The carbocation could be bonded to 2 other carbons, in which case it's classified as secondary. Or the carbocation carbon can be bonded to 3 other carbons. In that case, it's classified as tertiary. Oops. Tertiary. Okay, well, what difference does this make? I mean, we've seen this classification scheme before. We've seen it, for example, when we talked about the name of a tert-butyl group. Tert-butyl groups it's one of those branches that have branches, and the carbon there, the tert-butyl group is famous because it illustrates what happens when crowding is really important. This is a very crowded group. And the carbon there is bonded to 1, 2, 3 other carbons in the branch. And that's why it was called tert-butyl, because it was tertiary, bonded to 3 other carbons in the branch. So we've seen this sort of classification scheme before, and one of the things that make it significant are that it does tell you about crowding. So a tertiary carbocation is more crowded, for example, than a primary carbocation. But in the case of carbocations, there's another really crucial piece of information, and that's stability. A tertiary carbocation is the most stable of these 3 types of carbocations. And a primary carbocation is the least stable of these 3 types of carbocations. The reason why is because of the electron density that is around the carbons versus the hydrogens. Hydrogen has only 1 electron that it brings with it to the molecule. So if this carbon, its next door neighbor, it needs electrons, which it does because it has that positive charge. If it needs to borrow electron density to stabilize itself, hydrogen can't help it out very much. It only has 1 electron to donate. But a carbon has 6 electrons. It can donate more electron density to that positive charge to help to stabilize it. So the more carbons you have, the more electron density can be donated to the carbocation, and the more stable the carbocation becomes. This ends up becoming really, really significant throughout future chapters. And so what you'll want to ask yourself anytime you have a carbocation, and it's a very common mistake, people will get focused on the new material in other chapters, and they'll forget anytime you form a carbocation, always look to see if the carbocation would be more stable on an atom next door. And if it would, then a rearrangement has to occur to make that carbocation move. So for example, this carbocation here, this carbon that has the positive charge is just bonded to one other carbon. So that's a primary carbocation. Anytime you have a carbocation, look next door and ask yourself, if the carbocation were here, would it be primary, secondary, or tertiary? And it would be secondary. That carbon is bonded to two other carbons. And if it's more stable, then the carbocation ends up moving. So in this case, if it moves over one by a carbon, it becomes more stable. It goes from a primary carbocation to a secondary carbocation, which is more stable, because the carbons are able to donate more electron density to stabilize it. Now, you would never, ever, ever even think of drawing a curved arrow to move it. No, because curved arrows show the movement of electrons, and this positive charge is not electrons. Electrons have a negative charge. That positive charge is missing electrons. So instead, you take something that's next door and you move that. A hydrogen with two electrons is called a hydride. And so to move the carbocation, you end up having what's called a hydride shift. One of the hydrogens moves over, it shifts with its electrons. And that means that the positive charge is now where it left, on the carbon that it left behind. And you can see that new carbocation is secondary. So this is called carbocation rearrangement. You get carbocation rearrangement when a position immediately next to the carbocation is more stable than the position that the carbocation is on. You can get this rearrangement by moving a hydrogen, like we just saw. You can also get it by moving a methyl group. You could have a methyl shift. Now, you would only have the methyl shift if there's no hydrogen available. Oops. But if there's no hydrogen available, then you will get the methyl shift, and it makes the molecule look really different. And so you'd have the positive charge here. So notice how different the molecule looks. And notice if you're trying to predict a product based on where a nucleophile would attack, you have to think about the carbocation rearrangement. Because in this case, the nucleophile would attack a different carbon, a very different looking molecule than in the molecule on the left. Okay, let's get some practice with this in these exercises. So the first step is to look at where the carbocation is and decide whether that's primary, secondary, or tertiary. So this carbocation here is bonded to two other carbons, so it is secondary. What if it were on the left? Then it would be bonded to two other carbons. That would also be secondary. So that's not more stable, and so there's no reason for the carbocation to rearrange to the left. How about to the right? If the carbocation were there, it would be bonded to 3 other carbons. That would be tertiary. That is a more stable carbocation. The more carbons the carbocation is bonded to, the more stable it becomes. So there's going to be a rearrangement to show that secondary carbocation becoming a tertiary carbocation. To draw that, you want to draw in the hydrogen. There is a hydrogen here, an invisible hydrogen that's not being drawn. Only 3 bonds are drawn in, so the fourth must be a hydrogen. And so you get that hydride shift. The hydrogen with its electrons move over. The electrons attack the positive charge on that carbocation, and what you end up really doing is creating a new carbocation at the tertiary position. The hydrogen moved over, and now you have a tertiary carbocation. All right, let's think about it with B. So in B, we have this carbon that has the carbocation is bonded to to 3 other carbons. So that is a tertiary carbocation. If it moved to the right, that carbon is only bonded to 1 other carbon, so that would be a primary carbocation, much less stable, definitely not going to move there. If it moved to the left, that carbon is bonded to 1, 2 other carbons, so if it moved there, it would be a secondary carbocation, also less stable. If it moved down, that carbon is bonded to 1, 2, 3 other carbons. That's another tertiary carbon. So it would have the same stability that it has now, so there's no reason for it to move. So there's no carbocation rearrangement in B. Because no position immediately next door to the carbocation would create a more stable carbocation than the one that exists. Okay, for C, we'll do that same thing. So this carbocation, that carbon is bonded to 1, 2, 3 other carbons. That means that it is a tertiary carbocation. So pretty good, pretty stable. If it were to the right, that carbon is just bonded to 1 other carbon, so that would be a primary carbocation, much less stable. It's not going to move there. If it were to the left, that carbon is bonded to 1, 2 other carbons. That would be a secondary carbocation. It's also less stable in a tertiary. Now, if it were here, first of all, if it were there, one of the carbons would have to move. But you'll notice that that is bonded to 1, 2, 3, 4 carbons. You can't have a quaternary carbocation because a carbocation can have at most 3 bonds. That's why the carbon has that positive formal charge. So if it did move down there, it would still be a tertiary carbocation. The way it would move is one of these methyl groups would take its electrons and move over. You would get a methyl shift. Let's think about that scenario. What if you did have a methyl shift? You'd still have the methyl group that's there. You'd have a new methyl group that moved over. There'd only be one methyl group down here. Everything else stays the same. But you would have a new carbocation. Well, both the carbocation on the left and the carbocation on the right are tertiary. But the carbocation on the right is more stable because it's allylic to a lone pair. So not only is it tertiary, but it's being stabilized through resonance. Remember, if you have an allylic positive charge, the lone pair, the electrons in the pi bond move over toward the positive charge. And so that would give you this molecule here. So the true structure has the positive charge spread out over 2 atoms. And that resonance stabilizes the molecule even more than the carbocation being tertiary. And so you do get a carbocation rearrangement. And you end up getting the carbocation right next door. And notice how important that resonance is to predicting the product. If your nucleophile comes in, where will it attack? It'll either attack this carbon down here or the carbon on the other side. You would never have predicted that just looking at that. So you have to think about the carbocation rearrangement. Notice that also changes the carbon skeleton. And you have to think about resonance. And so that's the rearrangement you would get for C. For D, For D, we have this carbon with the carbocation that's bonded to 1, 2 other carbons, so that's secondary. If that moved to the right, that would still be 1, 2, secondary. If it moved to the left, it would still be bonded to 1, 2. It would still be secondary. So there's no reason for that carbocation to move because no matter where it goes on either side, it would be just as stable as it is now. So you'd have no carbocation rearrangement. For E, the carbon with the positive charge is bonded to two other carbons, so that's a secondary carbocation. To the right, if it moved there, that carbon is only bonded to one other carbon, so it would be primary. That would be a less stable carbocation. To the left, that carbon is bonded to 1, 2, 3 carbons, so if it moved there, that would be a tertiary carbocation. And so it's going to move to the left. Now, you would never draw the curved arrow showing the positive charge moving. Curved arrows show the movement of electrons. So what's the smallest thing on this left carbon? That's an implied hydrogen. There's a fourth bond there to the hydrogen that's not being drawn. That hydrogen can take up its electrons and move over to that hydride shift, and that would give you this new tertiary carbocation. This carbon with the positive charge is bonded to 1, 2, 3 other carbons. So that's the more stable carbocation, and so this is the curved arrow pattern that you would draw to illustrate that shift. F is really similar. You have your carbocation right now is bonded. That carbon is bonded to two other carbons, so it's secondary. If it moved to the right, on the right you have a carbon that's just bonded to one other carbon, so that would be primary, less stable. And to the left, you have a carbon that's bonded to 1, 2, 3, 4 carbons. Now, a carbocation can have at most 4 bonds, but what can happen is a methyl group here can move over. You can get a methyl shift, kind of like the hydride shift that we just saw. That methyl shift would lead to a different carbon skeleton. The carbocation would be on that new position. And notice that that carbocation is bonded to 1, 2, 3 other carbons. It's able to borrow the electrons from 3 other carbons. It's tertiary, it's more stable. And so you get this carbocation rearrangement in order to give you the more stable carbocation. In G, the carbon that has the positive charge is just bonded to one other carbon, so it's primary. Not very stable. Right next door, that carbon is bonded to 1, 2 carbons, so that's a more stable position. If the carbocation were there, it would be secondary. Now you would never draw the carbocation moving. Instead, you draw the smallest thing next door, which is a hydrogen, picking up its electrons and moving over. You get the hydride shift. Hydride is hydrogen with 2 electrons. And so the molecule you end up with is you have the hydrogen on the end, and you have the positive charge on that secondary carbon. Not only that, but notice that this positive charge is allylic, so it's actually going to spread out onto this bond and all of the bonds that are conjugated in that ring. It's a very stable carbocation. And finally for H, in H, this carbon with the positive charge is bonded to 1, 2, 3 other carbons, so it's tertiary. If it were to move to the right, it would still be bonded to 1, 2, 3 other carbons, so that's also tertiary. If it were to move up, it would only be bonded to one other carbon, so it would be primary. And there is nothing that can change places to the left. There's not a methyl group and there's not a hydrogen, so nothing can shift over to allow the carbocation to move to the left. So those are all the possibilities, and it's actually more stable if it stays where it is. Even though it's tertiary here it's tertiary. Not only is it tertiary, but it's allylic to the pi bonds in the ring. So it's actually spread out through resonance over all the atoms in the ring. And so, in this example, you would get no carbocation rearrangement. So, in general, when carbocations are carbons that have positive charges, they're classified as primary, secondary, or tertiary depending on how many carbons they're bonded to. The more carbons they're bonded to, the more electrons they can borrow from those carbons, and the more stable they become. The only thing more stable in a tertiary carbocation is an allylic carbocation, one that's one away from a positive charge. And any time in the future, and you'll see carbocations a lot, anytime you see one in the future, always look at all of the carbons next door and ask yourself, would it be more stable if the carbocation were there? And if it would be, you want to shift either a hydrogen or a methyl group over to move that carbocation. If you don't have a hydrogen or a methyl group on the carbon next door, then there's no shift. The carbocation stays where it is. But if there is one, then it moves over to give rise to a more stable carbocation.